Scientists may have just uncovered a hidden power source inside one of the most mysterious objects in the universe, a monster black hole. The discovery could change our understanding of how black holes create some of the most powerful cosmic jets ever observed. For nearly 2 centuries, astronomers struggled to make sense of a bright spot in the constellation Virgo. First described in 1781 by Charles Messier as a nebula without stars, it wasn't until the 20th century that scientists realized this object was in fact a massive galaxy, now known as Messier 87, or M87. Then in 1918, astronomers were stunned to find something even stranger, a narrow, bright jet of particles streaming out from the galaxy's center, moving at nearly the speed of light. For decades, the true engine behind this jet remained a mystery. At the heart of M87 sits M87 star, a black hole with a staggering 6.5 billion times the mass of our Sun. This giant not only warps space and time around it, but also spins rapidly on its axis. And as it turns out, that spin holds the key to one of the universe's most powerful engines. Using its enormous rotational energy, M87 powers a jet that extends more than 5,000 light-years into space. And this isn't unique. Similar jets are seen in other galaxies, all thought to be driven by rotating black holes. These cosmic outflows play a vital role. They spread energy and matter across space, influence how stars form, and even shape the evolution of entire galaxies. But one puzzle has remained. How exactly do black holes manage to launch these jets with such extreme power? Now, a team of astrophysicists at Goethe University Frankfurt believes they've found an answer. Led by Professor Luciano Rizzola, the researchers created an advanced simulation code known as the Frankfurt Particle-in-Cell Code for black hole spacetimes, or FPIC for short. This code allowed them to study, with unprecedented detail, how energy near a spinning black hole gets converted into these enormous particle streams. Until now, the leading explanation was the Blandford Znajek mechanism. In simple terms, it describes how strong magnetic fields can extract energy from a rotating black hole and funnel it into a jet. But the new simulations reveal something else is happening as well: magnetic reconnection. This process occurs when magnetic field lines near the black hole snap apart and reconnect, releasing bursts of energy in the form of heat, radiation, and streams of plasma. It's the same kind of process that drives solar flares on our Sun, but here, it's happening under extreme conditions near a black hole. Using millions of CPU hours on powerful German supercomputers, the team simulated how charged particles behave in these intense environments, taking into account both Einstein's theory of relativity and the equations of electromagnetism. The results were astonishing. In the equatorial plane of the black hole, the team observed intense reconnection activity forming chains of plasmoids, essentially bubbles of plasma moving at nearly the speed of light. These plasmoids don't just accelerate particles, they also create what scientists call negative energy particles, which may help siphon energy away from the black hole's rotation. In other words, the simulations suggest that magnetic reconnection is not just a side effect. It's actually an important way that black holes lose energy and power their spectacular jets. Dr. Filippo Camilloni, one of the researchers, explained it this way. Our results open up the fascinating possibility that the Blandford-Znajek mechanism is not the only astrophysical process capable of extracting rotational energy from a black hole. Magnetic reconnection also plays a role, Professor Rizzola added. With our work, we can demonstrate how energy is efficiently extracted from rotating black holes and channeled into jets. This helps explain why active galaxies can shine so brightly and why particles near black holes can reach such incredible speeds. This breakthrough is not just about one black hole. It provides a deeper understanding of how some of the brightest objects in the universe, known as active galactic nuclei, generate their extreme luminosities. It also gives astronomers better insight into the role black holes play in shaping the cosmos on a grand scale. For the scientists involved, there's also something deeply rewarding about combining raw computing power with elegant mathematics to peer into one of nature's most extreme laboratories. So, the next time you see an image of M87 star, the famous black hole first captured by the Event Horizon Telescope, remember this: hidden inside that shadowy abyss is not just a monster devouring everything in sight, but also a cosmic engine, powered by magnetic fireworks, capable of reshaping galaxies themselves. And thanks to new simulations, we may finally understand how these cosmic giants unleash their hidden power.